let's talk about rational functions and some of the common characteristics that they have. We're going to start by sketching the graph of our reciprocal function, f of x equals 1 over x. We graphed this a long time ago when talking about those toolkit functions, but I am going to go ahead and make a table of values just to help me remember what this shape looks like and plot some points. If I plug -2 in for x, I get 1 divided by -2, or -1/2. If I plug -1 in for x, I get 1 divided by -1, or -1. If I plug 0 in, well, 1 divided by 0 is undefined. 0 is actually not in the domain of this function. And then plug in 1, 1 divided by 1 is 1, plug in 2, 1 divided by 2 is 1/2. So I'm going to go ahead and plot those points. I've got the point, let's see, -2, -1/2, -1, 1, 1, 1, 2/2. And when I connect the dots, what's happening with this graph is as the x values are getting larger, the y values are approaching 0. We're getting fractions with magnitudes that are smaller and smaller and smaller. And the same thing is happening with negative values. As I plug in negative numbers with larger and larger magnitudes, those y values are approaching 0. In the middle of the graph, this function is actually undefined at x equals 0. What's happening is as we plug in smaller and smaller values for x, those y values are actually getting larger and larger. 1 divided by something that's really, really small gives us a very large output. And so the graph is approaching the y-axis, both on the right and the left side of x equals 0. So what we actually have here are known as asymptotes. As x goes to positive infinity on the right side of the graph, the y values are approaching 0. On the left side of the graph, the y values are also approaching 0. We can describe this behavior by saying y equals 0 is a horizontal asymptote. Again, that means the y values are approaching 0 at the ends of the graph. In the middle of the graph, we have another asymptote. And what's happening here is as we approach x equals 0 on the right side, the y values are going to infinity. As we approach x equals 0, the y values are getting really, really big. And as we approach x equals 0 on the left side, as we approach 0 coming in from the left, the y values are now going to negative infinity. And that's because x equals 0 is a horizontal asymptote. The function is approaching that line x equals 0, but never actually reaching it. So many rational functions are going to have asymptotes. And so just to summarize, we say that we have a vertical asymptote if as our x values approach that number, our y values go either to infinity or negative infinity. We have a horizontal asymptote if as our x values go to plus or minus infinity, our y values go to that value. So these are more formal definitions of asymptotes, but let's take a look at another example and see if we can graph and identify our asymptotes. So let's try to sketch the graph of f of x equals 1 over x plus 1 plus 3. Then give the equations of all asymptotes. Well, I can use my idea of graphing transformations to sketch this graph. I can start with my parent function, y equals 1 over x. That's what we just graphed in the previous slide. Y equals 1 over x goes through the point 1, 1. -1, -1 has a horizontal asymptote of 0 and a vertical asymptote of x equals 0. This plus 3 that is tacked on outside of the fraction is an output transformation. That's going to shift the graph up 3 units. The plus 1 that's inside the fraction is an input transformation. That's going to impact our x values. We do the opposite of what it says. So we're actually going to -1 from all of our x's, and that's going to take our graph and shift it to the left 1 unit. So I'm going to take this parent function, which I have drawn in blue, and I am going to move it up 3 units and to the left 1 unit. I like doing that by drawing in the asymptotes. That helps me kind of center my graph So notice my vertical asymptote moved left 1 unit. So there's the line x equal -1. My horizontal asymptote went up 1, 2, 3 units. It's now at y equal 3. And then I took a couple of the points on my parent function and I moved them up 1, 2, 3. Here we go. Let's try that again. 1, 2, 3, and then to the left, 1 unit. And so in black is a sketch of this function, f of x equals 1 over x plus 1 plus 3. And I can see where the asymptotes are. Those asymptotes were moved through my shifts. I have a horizontal asymptote of y equals 3. The graph is flattening out at the ends and approaching the line y equals 3. And I have a vertical asymptote of x equal -1. That is where my function is undefined, and those y values are going to positive infinity and negative infinity. All right, so let's see if we can summarize the important features of our rational functions without actually having to create a graph. So we're going to discuss finding domain, vertical asymptotes, horizontal asymptotes, and intercepts. If you want to find the domain of a rational function, this is actually something we've talked about before. It hasn't changed. The idea is division by 0 is undefined. We can't divide by 0. So if we want to find the domain of a rational function, we're going to take our denominator and say that that cannot equal 0. So in my first example, the denominator is x minus 4. X minus 4 cannot equal 0. I add 4 to both sides. I get x cannot equal 4. So the domain is every single number except for 4. 4 makes that denominator equal to 0. In interval notation, I would write that as negative infinity to 4, union 4 to infinity, making sure to use those parentheses with the 4 because 4 is actually not in that domain. Same idea works for the next function. I'm going to take my denominator, x squared minus 2x minus 3. That cannot equal 0. Denominator can't equal 0. This is something that we can solve by factoring. Product of -3, sum of -2 would be -3 and plus 1. So this factors as x minus 3, x plus 1. That means x cannot equal positive 3, and x cannot equal -1. So in interval notation, I've got negative infinity to -1, union -1 to 3, union 3 to infinity. Again, using those parentheses because we are not including the points at -1 and 3. Okay, so if we want to find the domain of a rational function, we always look at the denominator. Doesn't matter what's in the numerator, the denominator can't be 0 because we can't divide by 0. All right, well, what about asymptotes? How do we find asymptotes? Let's start with our vertical asymptotes. So vertical asymptotes are going to occur at zeros of the denominator as long as that 0 doesn't come from a common factor. So this will be easiest for me to explain with some examples, but I do have kind of a summary here typed up on the screen. If we want to find vertical asymptotes, we're going to factor everything as much as possible. This is a good time to note any restrictions in the domain, the idea that the denominator can't equal 0. We're going to reduce the expression by canceling common factors. After we reduce, then zeros of the denominator are places where our vertical asymptotes occur. If we have restrictions in the domain where asymptotes do not occur, those are actually going to be holes in the graph or removable discontinuities. All right, so again, I think this will be easier for me to explain by showing you an example. So if I want to find vertical asymptotes, the first thing I'm going to do is see if I can factor my numerator and or my denominator. So in my first example, I have the function f of x equals 4x divided by x plus 3. I can't factor this at all, so all I'm going to do is take my denominator, x plus 3, set it equal to 0, and solve. X plus 3 equals 0 when x equals -3. So -3 is going to be a vertical asymptote. If we plug negative 3 into this function, we're going to get 0 in the denominator. That means the function is going to be going to infinity or negative infinity. Let's compare that to my second example. In my second example, we have the function f of x equals 2x minus 6 divided by x squared minus 9. My first step is to factor as much as possible. And in this case, I can factor the numerator by pulling out a 2. We've got a common factor of 2 in the numerator. So if I pull that out, I'm left with 2 times x minus 3. And the denominator is a difference of perfect squares, x squared minus 9. That can be factored as x plus 3, x minus 3. Now notice that we have a common factor of x minus 3. If you have a common factor, something that exists in both the top and the bottom, that is going to actually be a place where you have a hole in the graph or a removable discontinuity. To find my asymptote, I only look at factors of the denominator that are not part of common factors. So the only thing I'm going to look at here is the x plus 3. I set it equal to 0. X plus 3 equals 0 when x equals negative 3. So x equal negative 3 is a vertical asymptote. So vertical asymptotes occur at zeros of the denominator as long as that 0 comes from something that's not a common factor. That x minus 3, because that is a common factor, that actually means that we're going to have a hole in the graph at x equal 3. And holes are sometimes referred to as removable discontinuities. All right, what about horizontal asymptotes? The kind of horizontal asymptote we have is going to depend on the degree of the numerator and the degree of the denominator, degree being that largest power of x. So the first situation would be the degree of the numerator is smaller than the degree of the denominator. An example would be x, which has a degree of 1, divided by x squared plus 1, which has a degree of 2. Anytime the degree of the numerator is smaller than the degree of the denominator, the line y equals 0 is going to be a horizontal asymptote. And to explain why, the end behavior is always determined by our leading terms, our largest powers of x. So the end behavior of this function is going to be determined by x divided by x squared. And x divided by x squared simplifies down to 1 over x. If you plug in a really, really big number for x, 1 divided by a huge number is going to go to 0, and y equals 0 is our horizontal asymptote. Okay, so anytime the degree of the numerator is smaller than the degree of the denominator, that denominator is growing much faster than the numerator, and the function is going to approach y equals 0 when x is very large. The second situation we might have is when the degree of the numerator is equal to the degree of the denominator. An example would be f of x equals 2x plus 1 divided by 5x plus 3. In this case, the degree of the numerator is 1, and the degree of the denominator is also 1. So they have the same degree. To find our horizontal asymptote, again, we can think about the leading term, the largest power of x, in the top and the bottom. When x gets really, really big, this function is going to approach 2x divided by 5x, which simplifies down to 2/5. So y equals 2/5 is my horizontal asymptote. And so our horizontal asymptote is always going to be the ratio of those leading coefficients. So leading coefficient 2 over 5, y equals 2 is my horizontal asymptote. Finally, the third thing we might see is the degree of the numerator could be bigger than the degree of the denominator. For example, x squared divided by x plus 4. In this situation, there's actually going to be no horizontal asymptote. If you take your leading term in the top, in this example it was x squared, divided by the leading term in the bottom, in this case x, That simplifies down to x. If I plug in a really, really big number, that's actually going to go to infinity. It's not going to approach a finite number. So this is a situation where we have no horizontal asymptote. All right, let's see if we can put this together and do some examples. Find all horizontal asymptotes. So my first example, 4x minus 3 over 2 minus x. This is the second situation where the degree of the top and the degree of the bottom is the same. So if I look at those leading terms, largest power of x, 4x divided by negative x simplifies down to negative 4. That means y equals negative 4 is my horizontal asymptote. Second example, we have the function f of x equals 5x plus 2 divided by x squared plus 1. In this case, the degree of the top is smaller than the degree of the bottom. If I look at those leading terms, 5x divided by x squared, that simplifies to 5 divided by x. If we plug in a really big number for x, that is going to go to 0, and y equals 0 is my asymptote. All right, so anytime the degree of the top is smaller than the degree of the bottom, it's always going to have an asymptote of y equals 0. Finally, my last example, f of x equals x cubed plus 3x divided by x squared minus x minus 2. This is a situation where the degree of the top is bigger than the degree of the bottom. Third degree polynomial on the top, second degree on the bottom. And so that means we are going to have no horizontal asymptote. Okay, so vertical asymptotes are zeros of the denominator, as long as they don't come from a common factor. Horizontal asymptotes are related to the degree of the numerator and the denominator, and horizontal asymptotes really are describing our end behavior of our function. Now, in that third case where we don't have a horizontal asymptote, sometimes we have a slanted asymptote. So I have graphed on my computer the function f of x equals 2x squared minus 5x plus 3 divided by x minus 2. And if I take a look at the ends of the graph, there's no horizontal asymptote. They're not approaching a horizontal line. I know that's going to happen because the degree of the top is bigger than the degree of the bottom. Instead, I see a slanted asymptote. The ends of the graph are approaching a line, but it's actually not a horizontal line. If we want to figure out what this slanted asymptote is, we can use division. You can use synthetic division or long division. I'll go ahead and use synthetic division. So my numerator was 2x squared minus 5x plus 3. So I jot those numbers down. If I'm dividing by x minus 2, I write down a positive 2. Bring down the 2. 2 times 2 is 4. Add, I get negative 1. Negative 1 times 2 is negative 2. Add, I get 1. So what this quotient, what this division is telling me is that I can rewrite this function as 2x minus 1 plus my remainder, which was 1, divided by x minus 2. So this rational function that we started with is equivalent or equal to the line 2x minus 1 plus 1 over x minus 2. The slant asymptote is always going to be your quotient. So in this case, the 2x minus 1. My slant asymptote is the line y equals 2x minus 1. That's because the remainder, as x gets really, really big, that remainder is going to go to 0, and we're just going to be left with that line, y equals 2x minus 1. So if you want to find a slant asymptote, you can use synthetic division or long division. You ignore the remainder, and your answer is just the quotient. That is your asymptote. All right, let's see if we can put all of this information together and sketch a graph. So we've got the rational function f of x equals x minus 1 divided by x plus 2. We're going to find all of the asymptotes, then we'll find intercepts, and then finally, we'll put all of that information together and draw our picture. All right, so to find my vertical asymptote, I notice that I can't do any factoring, so I'm just going to take my denominator, x plus 2, and set it equal to 0. That gives me x equal negative 2. So I have a vertical asymptote at x equal negative 2. For my horizontal asymptote, this is case 2. The degree of the numerator and the degree of the denominator is equal. And so if I take those leading terms, those largest powers of x divided by x is 1. So y equals 1 is my horizontal asymptote. All right, to find the intercepts, we're going to plug in 0. To find my x-intercept, I'm going to plug in 0 for y. And if I plug in 0 for f of x, I actually get 0 equals x minus 1 over x plus 2. The only way a fraction can equal 0 is if the numerator equals 0. So if you want to find an x-intercepts are going to occur at zeros of the numerator. Vertical asymptotes occur at zeros of the denominator. X-intercepts occur at zeros of the numerator. So I set my numerator equal to 0, solve for x, I get x equal 1. So I have an x-intercept at 1. To find my y-intercept, I just plug in 0 for x, and I get negative 1 divided by 2. So my y-intercept is the point 0, negative a half. My x-intercept is the point 1, 0. Finally, let's put this all together and draw a graph. So to graph a rational function, I usually like drawing in my asymptotes first. So I've got a vertical asymptote, x equal negative 2, and my horizontal asymptote is y equals 1. Those asymptotes are going to help me guide my graph. Then I'm going to plot my intercepts. I have a y-intercept at 0, negative a half, and an x-intercept at 1, 0. So I can connect those points, and I want to make sure that on the right side of the graph, my line, my curve, is approaching my horizontal asymptote. And then I'm going to have, on the left side there, I'm going to draw the graph so it's approaching that vertical asymptote. I know that the curve goes down towards the vertical asymptote and not up because there's no other intercepts. It can't cross the axes again, so it has to go down towards that asymptote. There's going to be another half of the graph, and to help me figure out where the rest of the function is, I am going to try to plot another point to the left of this asymptote. So I have a vertical asymptote at negative 2. I decided to choose negative 3. I'm just going to choose any number that's smaller than negative 2. I'm going to plug that into my function just to guide my graph, give me another point to plot. So I took negative 3 and I plugged that into the function. I got negative 3 minus 1, that's negative 4, over negative 3 plus 2, that's negative 1. That simplifies to 4. So if f of negative 3 is 4, that means my graph has to contain the point negative 3, comma 4. And so I'm going to draw this so that as I go towards x equal negative infinity, the graph goes down towards my horizontal asymptote, and then I'm going to have it go up towards my vertical asymptote. And there's a rough sketch of this rational function. All right, let's take a look at another example. Let's see if we can find all asymptotes, find all holes, find all intercepts. I have the function f of x equals x squared minus 3x minus 10 divided by x squared plus x minus 2. I'm going to start by factoring as much as I can. And the numerator can be factored because product of negative 10, sum of negative 3, would be negative 5 and positive 2. So I can factor the numerator as x minus 5, x plus 2. I can also factor the denominator. Product of negative 2, sum of 1, would be 2 times -1, or x plus 2, x minus 1. So now I notice I do have a common factor of x plus 2. That is a hole in the graph. That's not going to give me an asymptote or an intercept. I look at x minus 1. That is the only factor in the denominator that can't be canceled, that isn't part of a common factor. And I set that x minus 1 equal to 0. I get x equal 1. So I have a vertical asymptote at x equal 1. To find my horizontal asymptote, I look at my leading terms. Largest power in the numerator is x squared. Largest power of x in the denominator, also x squared. X squared divided by x squared is 1. So y equals 1 is my horizontal asymptote. Since I have my function in factored form, I can find my hole or my removable discontinuity by looking at that common factor. That common factor x plus 2 equals 0 when x equals -2. So that tells me there's a hole at x equal -2. To find my intercepts, my x-intercepts are going to occur at zeros of the numerator as long as we're not talking about the hole. The common factor is a hole. It's not going to give you an asymptote or an intercept. So to find my x-intercept, I just look at the x minus 5. X minus 5 equals 0 when x equals 5. So the point 5, 0 is my x-intercept. To find my y-intercept, I plug in 0 for x. So the numerator, I got 0 minus 10. And the denominator, I got 0 plus 0 minus 2. Minus 10 divided by minus 2 is 5. So I have a y-intercept at 0, 5. Okay, so common factors are holes. Zeros of the denominator are vertical asymptotes. Zeros of the numerator, x-intercepts. For my last example, I want to work backwards. So now we're given a picture or a graph of a rational function. Let's see if we can come up with an equation that matches this graph. I'm going to start by identifying my asymptotes. We have a vertical asymptote at x equal -1. I have a horizontal asymptote of y equal +1. So that, oh, and then one more thing, let's identify our intercept as well. It looks like we have an x-intercept at 2, 0. So let's see if we can use this information to create our graph, or our equation, I should say. So if we have a vertical asymptote at x equal -1, x plus 1 has to be my denominator. Vertical asymptotes are zeros of the denominator. So I have to have a factor of x plus 1 in my denominator. My x-intercept is at 2. X-intercepts are zeros of the numerator. So that means x minus 2 has to be in my numerator. All right, so is this it? Or should there be any other constants in this problem? To determine that, I am going to look at my horizontal asymptote. We need to have a horizontal asymptote of 1, and I'm going to check, does this have a horizontal asymptote of 1? Oh yeah, because if I look at my leading terms, x over x becomes 1, so this does have a horizontal asymptote of 1. If I wanted to have a horizontal asymptote of 2, I could just put a GCF or a factor of 2 in front of the x minus 2. But we don't have to do that. X divided by x gives us 1. So this function matches the graph that is given. All right, that was my last example. Please let me know if anything in this video is unclear.